So let's take a look at triple integrals. And so Fubini's theorem for triple integrals states that if we have the triple integral, let's say it's described by the region of the rectangular box B of some multivariable function. This time we have three input variables, f of x, y, z, since it's a triple integral, and we have dv, which stands for the volume. Now in double integrals we had dA, which stood for the area, because we just took the x distance times the y distance to get the area of a rectangle. But this time we have to take the x distance times the y distance times the z distance to get us the volume. And so the theorem states that, let's say the function f is continuous on the rectangular box which has the dimensions. The x values go from a to b, the y values go from c to d, and the z values just go from r to s. And so the theorem states that the triple integral of the function dv is going to be equal to the triple integral. So now we're going to insert our bounds in. So the x bounds will just go on the inside from a to b, followed by the y bounds c to d, and the z bounds from r to s, of the multivariable function f of x, y, z, times, well, we have dx on the inside integral, dy, and then dz. So let's go ahead and evaluate the iterated integral. So for number 1, we have the integral, or the triple integral, from 0 to 1, from 0 to z, and from 0 to x plus z, of 6 times x times z, dy, dx, dz. So this is going to be evaluated the same way as we would evaluate a double integral. We just have an extra step because of an added integral. So let's just go ahead and write the inside integral from 0 to x plus z of 6xz dy. Now we're integrating with respect to y. So the integral of 6xz with respect to y is just 6xz times y. Now let's go ahead and evaluate that from 0 to x plus z. Those are once again going to be the y bounds. So when I plug in x plus z, we'll get 6xz times x plus z minus, when I plug in 0, I'll just get 0 for y. Now x plus z minus 0 is just x plus z. And so we have 6xz times x plus z. Now I'm actually going to go ahead and distribute over the 6xz. So we'll get 6x squared z plus 6xz squared. So now the middle integral is from 0 to z. Now we're going to integrate with respect to x. So the integral of 6x squared to z is going to be 6x cubed over 3 times z plus 6x squared over 2 times z squared. Now if I simplify, the 6 over 3 is 2, and 6 over 2 is 3. So then we'll get 2x cubed z plus 3x squared z squared. Let's go ahead and evaluate that from the x bounds of 0 to z. So when I go ahead and plug in z for x, we'll get 2 times z cubed times z plus 3 times z squared times z squared. Minus, when I plug in 0, we'll just get 0 plus 0. So that will cancel. And so we're left with 2z to the 4th plus 3z to the 4th. And so that will give us 5z to the 4th. So now the very outer integral is from 0 to 1 with respect to z. So we're going to take the integral from 0 to 1 of 5z to the 4th with respect to z. Now the integral of 5z to the 4th is 5z to the 5th over 5, which is just z to the 5th. So now we can go ahead and evaluate that from the z bounds of 0 to 1. So when I go ahead and plug in 1 for z, we'll just get 1 to the 5th, which is 1, minus when I plug in 0 for z, we'll get 0, so the final answer is 1. So now for number 2, let's go ahead and evaluate the triple integral from 0 to 3, from 0 to 1, and from 0 to the square root of 1 minus z squared of z times e to the y times dx, dz, dy. So let's go ahead and evaluate this. So I'll write the inside integral first, from 0 to the square root of 1 minus z squared of z times e to the y, and we're going to integrate with respect to x. So the integral, since z times e to the y is just a constant, is going to be z times e to the y times x. Let's go ahead and evaluate that from the x bounds from 0 to 1 minus z squared. So when I plug in 1 minus the square root of 1 minus z squared for x, we'll get z times e to the y times square root of 1 minus z squared, minus, when I plug in 0 for x, we'll just get 0. So then we're left with z times e to the y times the square root of 1 minus z squared. So now let's go ahead and evaluate the middle integral from 0 to 1 with respect to z. And so e to the y in this case is just a constant. We can also take that outside of the integral and rewrite it as e to the y times the integral from 0 to 1 of z times the square root of 1 minus z squared dz. Now this is just a u substitution problem. So I'm going to set u equal to 1 minus z squared. So then du, or the derivative of 1 minus z squared, is going to be equal to negative 2z dz, so we derive with respect to z. And if I go ahead and isolate z, dz is going to equal du over negative 2z. Now if I go ahead and plug that back into the integral, we get e to the y times the integral from 0 to 1 of z times, well, we made u equal to 1 minus z squared. So I'm going to rewrite it as u to the 1/2 instead of the square root of u times dz, which is equal to, once again, du over negative 2z. Notice the z's will cancel. Negative 1/2 can come outside the integral as a constant, so we get negative 1/2 times e to the y times the integral from 0 to 1 of u to the 1/2 du. Now the integral of u to the 1/2, let's go ahead and write the constant first. We have negative 1/2 e to the y times the integral of u to the 1/2 is 2/3 u to the 3/2. Now negative 1/2 times 2/3 is negative 2/6 or negative 1/3. So we get negative 1/3 times e to the y times u to the 3/2. Now u is equal to 1 minus z squared. So I go ahead and substitute back in 1 minus z squared all to the 3/2. Now let's go ahead and evaluate from the z bounds of 0 to 1. So when I go ahead, I'll write the constant first, 1 over 3 e to the y times, now when I plug in 1 for z, we'll get 0, minus, when I plug in 0, we'll get 1 to the 3/2 or 1. Now 0 minus 1 is negative 1, the negatives will cancel, and so we're left with 1/3 times e to the y. So now I can go ahead and finally evaluate the outer integral from 0 to 3 with respect to y. So the integral of 1/3 e to the y is just 1/3 e to the y. If I evaluate that from the y bounds of 0 to 3, I'll write 1/3 first. When I plug in 3 for y, we'll get e cubed. When I plug in 0, e to the 0 is 1. So we're just left with 1/3 times e cubed minus 1 as the final answer. So for these next set of problems, let's go ahead and evaluate the triple integral. So for number 1, we have the triple integral of 2x dv described by the region E, where E is in set notation for all x, y, z ordered pairs, such that the y values range from 0 to 2, the x values range from 0 to the square root of 4 minus y squared, and the z values range from 0 to y. So we just have to turn this into an iterated triple integral and then evaluate from there. So if I rewrite the integral here of 2x, now remember that whichever of the bounds contain variables, those are the ones we usually put on the inside integral. So since x goes from 0 to square root of 4 minus y squared, let's go ahead and just put that on the inside first. So from 0 to square root of 4 minus, let's write that a little bit bigger here, square root of 4 minus y squared. Since those are the x bounds, I'll put dx on the inside. Let's go ahead and just put from 0 to y for the z bounds next. So I'll put dz, and then finally the y bounds are constant, so that will go last from 0 to 2. So we have dy on the outside. So now we can go ahead and evaluate this integral. So we have the integral from 0 to square root of 4 minus y squared of 2x dx. So the integral of 2x is obviously just x squared. Let's go ahead and evaluate that from the x bounds of 0 to square root of 4 minus y squared. Now when I plug in square root of 4 minus y squared for x, we'll get the square root of 4 minus y squared squared, which is just 4 minus y squared. When I plug in 0, I'll just have minus 0. So we're just left with 4 minus y squared. Now we can evaluate the middle integral from 0 to y with respect to z this time. So the integral of 4 with respect to z is just 4z, minus the integral of y squared with respect to z is y squared times z. We can go ahead and evaluate that from the z bounds of 0 to y. So when I plug in y for z, we'll get 4y minus y squared times y, which is just y cubed, minus when I plug in 0, we'll just get 0 times 0, or 0 minus 0. So that will just be 0. So given that we're left with 4 minus y cubed, let's go ahead and evaluate the outer integral from 0 to 2 with respect to y. Now the integral of 4y is just 4y squared over 2, or 2y squared, minus the integral of y cubed is y to the 4th over 4, or 1/4 y to the 4th. So now let's go ahead and evaluate that from the y bounds of 0 to 2. So when I plug in 2 for y, we'll get 2 times 2 squared, which is 2 times 4, which is 8, minus, we'll get 2 to the 4th, 16 over 4 is 4, minus when I plug in 0, we'll just get 0 minus 0. That will cancel, and so we're left with the final answer of 8 minus 4, which is 4. So now for number 2, we have the triple integral of 6xy dv described by the region E, where E lies under the plane z equals 1 plus x plus y, and above the region in the xy plane bounded by the curves y equals the square root of x, y equals 0, and x equals 1. So I can start off by rewriting the triple integral of 6xy. So now let's go ahead and find the bounds of integration. So I'm going to go ahead and start off with the z bounds, because we know the region E lies under the plane, so lies under 1 plus x plus y, but it lies above the region of the xy plane. Now the xy plane is obviously where z equals 0. So right now we're trying to go from z equals 0 all the way to z equals 1 plus x plus y. So those are going to be our z bounds. So if I write it in inequality here, it's going to range from 0 to 1 plus x plus y. Now in order to find the xy bounds, all we have to do is draw out this region here. So notice that it's bounded by the curves y equals the square root of x, looks something like this, y equals 0, the x-axis, and then we have x equals 1. So this is basically the region we're looking for here. Now realize the x values basically range from 0 to 1, so we can say that in an inequality the x bounds are from 0 to 1, and the y bounds, notice it goes from the equation y equals 0 all the way up to the equation y equals square root of x. So those are going to be our y bounds. We're going to say the y bounds go from 0, or y equals 0, to y equals the square root of x. So once again, when we put in our bounds into the integral, we're going to put the ones with the variables first, or in the inside. So I'm just going to go ahead and put the z bounds first, from 0 to 1 plus x plus y, and dz. Next I'll put the y bounds here, from 0 to the square root of x, and then I'll put dy there. And then we have the x bounds, obviously, from 0 to 1, so I'll put dx on the very outside. So now we can go ahead and actually evaluate this integral. So if I rewrite the inside integral from 0 to 1 plus x plus y of 6xy, and we're going to integrate with respect to z, since this entire thing is a constant, the integral is just going to be 6xy times z. Let's go ahead and evaluate that from the z bounds of 0 to 1 plus x plus y. So when I plug in 1 plus x plus y for z, we'll get 6xy times just 1 plus x plus y, minus when I plug in 0, we'll just get 0. So we're left with 6xy times 1 plus x plus y. Now I'm actually going to go ahead and distribute it over. So then we'll get 6xy plus 6x squared y, and then plus we get 6x y squared. So now we can evaluate the middle integral from 0 to the square root of x. Once again, those are y bounds. So we have dy. Now the integral of 6xy is going to be 6xy squared over 2. Integral of 6x squared y is going to be 6x squared y squared over 2. If I rewrite the y squared. And then plus the integral of 6xy squared, we get 6xy cubed over 3. Now we can go ahead and simplify all these. So 6 over 2 is 3xy squared plus, once again, 6 over 2, 3x squared y squared plus 6 over 3, which is 2xy cubed. So now we can evaluate it from the y bounds of 0 to the square root of x. So now when I plug in square root of x for y, we'll get 3x times square root of x squared, which is x, plus 3x squared. Once again, x squared of x squared is x, plus 2x. Square root of x cubed is x to the 3 halves power. Since 1 half, x to the 1 half to the third is to the 3 halves. So then when I simplify, we'll get 3x squared plus 3x cubed, and then plus 2x to the first times x to the 3 halves. We just add the powers, is x to the 5 halves. So then minus, when we plug in 0 for the y bound, we'll get 0 plus 0 plus 0. So that will just cancel. So we'll end up getting 3x squared plus 3x cubed, and then plus 2x to the 5 halves power. So now finally we can evaluate the outer integral from 0 to 1 with respect to x. So the integral of 3x squared is just 3x cubed over 3, or x cubed, plus the integral of 3x cubed is 3x to the 4th over 4, then plus the integral of 2x to the 5 halves is 2 times 2 over 7 x to the 7 halves. Now we can simplify that down to x cubed, once again plus 3/4 x to the 4th power, plus 2 times 2 over 7 is 4 over 7, x to the 7 halves. Let's go ahead and evaluate that from the x bounds of 0 to 1. So when I plug in 1 for x, we'll get 1 plus 1 to the 4th times 3/4, which is 3/4, and then plus 4 over 7. Minus, when I plug in 0, we'll just get 0 plus 0 plus 0. So that will cancel. And so we're left with 1 over 1 plus 3 over 4 plus 4 over 7. If I go ahead and combine all three of these into one whole fraction, common denominator is 28. So we get 28 over 28 plus 3 over 4 can be turned into 21 over 28. And then plus 4 over 7 can be turned into 16 over 28. So then 28 plus 21 is 49, and 49 plus 16 will give us a final answer of 65 over 28.